Hello everyone, welcome to what will be pre-lecture 5 for our class on Wednesday, August 31st. Just a remember, or a reminder to subscribe to the video if you want, like it I guess if you want, but if you want to subscribe to my channel, that way you'll know exactly when I post these pre-lecture videos. Okay, so these are what you should know by the end of class. We're going to talk about what a mole is, as well as ionization energies and atomic and ionic radii today. So what is a mole? Hopefully it's something you've heard of, not only because of the animals, but as a way to count. And so obviously atoms and molecules are very, very, very small. And so in order to work with them at a human-sized level, we need a lot of atoms or a lot of molecules. And the most convenient way we have determined to do this is to use something called a mole. And so a mole of something is exactly like if you have a dozen of something. So if you have a dozen of something, you have 12 of them. If you have a mole of something, that just means you have 6.022 times 10 to the 23rd of something. It's kind of like saying we have a trillion of something to give you a scale of the idea. And that number, the 6.022 times 10 to the 23rd, we call Avogadro's number. And so I'll be using that in class and throughout the rest of the semester. But it's essentially how we get between a mole of something and count how many things there are. Okay? As a side note, I would highly recommend that you read what would happen if you had a mole of moles, a mole, the counting number, and then a mole, the animal. So what would happen if you had a mole of moles on the website XKCD. I put a link down here, so if you click that on the slides, it gives you a really good sense of how much a mole really is. And just as a preview of that, this is the Earth with our mantle, our crust. If we had a mole of moles, that's Mount Everest, and we would have approximately 40 miles of moles covering the surface of Earth, which is a lot, obviously. Anyhow, moving on to ionization energies. So this is something back in our textbook, chapter 3, and last time we talked about what happens when electrons get excited by radiation and then emit that radiation. Once they relax back down, they emit light. But what happens if the n energy level that we excite an electron to is infinity? In that case, we would just say that the electron has been removed from the atom, and that atom then becomes an ion. The ionization energy is the term that we give to this, and it is the smallest amount of energy needed to remove an electron from a neutral atom of that element in the gas phase. And typically what we care about most is the first ionization energy. For the rest of this PowerPoint, I'll also abbreviate it as IE. And it is most commonly the most commonly reported value and usually requires either UV or X-ray radiation. And so these are some of the values from the first 20 elements shown in your textbook. So you can see here like hydrogen, helium, lithium, and we're going to talk some more about the trends in these ionization energies. And that can be seen pretty clearly in this graph. So these are the 20 elements just shown in a different way, where we have energy on our y-axis here and the atomic number on our right, or on our x-axis, excuse me. And so what you see here is hydrogen as our starting point, and then we go to element number 2, helium. Our electron, or our first ionization energy goes way up, right? It adds about 1,000 kilojoules per mole. Then, surprisingly, things go way back down for helium. And then we kind of climb back up another mountain, the next 8 elements, and then we go back down. Climb back up and go back down. And so why is that? Ultimately, it's going to be related to how closely our nuclei hold on to those electrons. So we talked about that a little bit last class. We're going to talk about it more in this class. And let's just use the first 3 elements as an example. So hydrogen, helium, and lithium. As there are more protons, we would expect that the electrons would be held closer and closer to our nucleus. But what happens after we add 2 electrons to helium and we go to lithium, where we have 3 protons, is we see this huge drop in our first ionization energy. And so we need a theory to explain why that is. And that's where the idea of a shell model comes in. And so we would say that lithium's last electron, that third electron, occupies a new shell that is going to be further away from our nucleus, and thus that electron will become a lot easier to remove. And so, for example, we have our nucleus here, our inner shell that can hold 2 electrons, and then our second shell, which for lithium only has that 1 electron, that becomes very easy to remove. And this is something that basically tracks on the periodic table then. So our first 2 elements have their own row to themselves. Then our next 8 elements are all in a row together. Then our next 8 elements are all in a row together. And you can kind of see the trend that occurs there. However, as we go across the row, so for example, if we go from lithium to boron to oxygen to neon, what happens is our atomic radius gets smaller and smaller. And so as that radius is getting smaller, our ionization energy goes back up. And that is because, again, our electrons are going to be closer in to our nucleus. Our nucleus is also going to have a higher charge value. So the higher the charge, the closer our electrons get held until we add a new shell. So when we transition from neon to sodium, we start a new shell, something like this. This is actually our transition or comparison between sodium and potassium, where our shell gets a little bit bigger and that first electron becomes a little bit easier to remove. Okay? That's going to be all for our pre-lecture, so hope that was informative, and if you do have any questions, please let me know. Otherwise, I will see you in class.